So yeah, we'll probably begin then. Yeah, so we're looking at the attention section, which is actually one of the most interesting ones today. So yeah, if we start from that, and then we'll catch up at about 50 minutes past. Is that okay?
Hey, Arshad.
Yeah. Hey, how you doing?
Yeah, so we're starting from attention is all you need, yeah?
I think it's attention mechanisms, isn't it? Is that, or is that a little bit too early?
Attention mechanism, where is it? Which one?
Oh, actually, attention is all you need is a little bit further forward, isn't it?
Okay, yeah. Okay, yeah, attention mechanism.
Yeah, I
Yeah.
wouldn't mind starting there because unfortunately I missed the weekend, and
No, that's fine.
it's only about 3 pages, I think,
Oh, yeah,
before
absolutely right.
the bit.
Absolutely right. Yeah.
Yeah, and we'll catch up at about 50 minutes past. Is that okay, guys?
And are we aiming to finish it off or?
Yes, that's the aim.
Okay, fantastic. Yeah. 50 past is the time. Yeah, sure.
Okay, thanks then. Right, speak
Talk
to
to
you
you
in a
then.
bit.
Cheers.
Right, bye. Oh, hey guys.
Hey.
Oops. Let me turn off my. Oops. Trying to do the wrong thing there. Let me see. Can you guys see my screen? Yet?
Yeah.
Yes.
Yeah, so we can probably quickly go through the attention mechanisms, because did you guys both attend the Sunday session?
Yeah, I did.
I didn't attend it.
Yeah, we'll quickly go through this attention mechanism section, not to bore Dinesh too much, and then we'll go to the attention is all you need.
I'm telling you, you can spend the whole lecture on it. I'm more than happy to listen.
Yeah, I mean, these attention mechanisms, they're just really, really interesting, and sometimes they're really hard to get your head around. Okay, so let's get started, because this is actually quite a dense bit of the book. Oops. Let's go. Yeah. So we start with. Okay, so let's say that we're actually looking at translation, and we're looking to translate the word milk to its French variant, lait. But the potential mechanism to go from milk to lait might be a little bit convoluted, because it depends on the context in which the word milk was used as to whether this is exactly the correct translation. And so they said, so this means that a representation of this word along with all the other words needs to be carried over many steps before it is actually used. So essentially, we're interested in the context when we're getting ready to translate this, and obviously, we don't want to have to carry all that context around with us. So they ask a question: can't we make this path shorter? So this fellow Dmitry Badenow in 2014 introduced this interesting concept. So they introduced a technique that allowed the decoder to focus on the appropriate words as encoded by the encoder at each step. Yeah, so instead of specifically for that word milk carrying some context, they've introduced a mechanism where at any particular point you can focus on whatever you need, as it were, in the whole sentence to be able to do what you need to do. And they said attention mechanisms revolutionized neural machine translation and NLP in general, allowing a significant improvement in the state of the art, especially for long sentences over 30 words. Okay, so that's just a little bit of a plug for them. So this is a kind of a little diagram of how this was this works in an encoder decoder kind of environment. So normally in an encoder decoder, what you would do would be to take the input, pass it through the encoder layer one step at a time, eventually coming out with a hidden state. And then you use that final hidden state to drive the decoder. Well, here, things are now a little bit more different in that we're going to use the hidden state at each point to actually generate a more complex calculation, which is the attention. And they're going to give a little bit of description here.
Just one quick question before you go ahead. And if you remember last time we were saying, or maybe it was in a Sunday they were discussing, in the previous section, they mentioned that initially they said, oh, we have to put the sequence in a reverse direction rather than I drink milk. In the encoder, it should go like a milk drink I.
Yeah,
so I didn't capture that, grasp that, and it was, I think, controversy there. Would you have any idea why in a previous section they wanted to have milk drink I going into the encoder?
I mean, I'm kind of guessing here, but I mean, if you kind of think about it, I mean, I can understand exactly where you're coming from, because eventually the encoder is going to generate a hidden state. And so the question is the hidden state somehow easier to compute or better if you put the data in one direction than in another direction? And I can sort of understand that maybe the hidden state is a little bit easier or better if you do it the other way around, because I mean, let's say you're translating that sentence, milk is great. When you start to translate it, really the first word you're interested in looking at is milk. But in an encoder-decoder architecture, milk appeared a long time ago. I mean, let's say this was like a much bigger sentence. Yeah, it had like 30 words in it or something. Then the sentence that started the whole thing off was a very, very long time ago, because the final hidden state you've got is like now much, much later than where you started. So if you do it the other way around, then it means that the final hidden state has got the most recent info that it needs at its fingertips, as it were, because milk was what is like what it needs to get the whole thing started. So I can sort of understand, that potentially it might be better, but they'd have to prove to me that the other way is significantly worse, because as you say, it all depends on how complex the hidden state is. Well, if the hidden state is sufficiently complicated, then it shouldn't matter what direction you do it.
Well, I thought it should have been just the opposite, because when you say I drink milk, so when you time step I, first is processing I, and then time process the drink is the second one, and milk is the last one. So milk, the hidden state, the milk is sitting on the top of the stack. So my understanding was when we send the final hidden state to a decoder, milk is actually, if we read it right, I drink milk, milk is actually the first or last of the decoder, last of the encoder, that is the first for the decoder. So I thought milk is very close. The milk itself is the last word of the encoder, is the first to a decoder, and I thought that's the right way of doing. So milk is not far away; it's rather a nearer one.
Sorry, Dinesh, I don't fully understand. So let's say you had milk as the first word, and this was a sentence with 30 words in it. I don't know what that would be. And then you want to now translate that to French. So what were you saying? You're saying, it should look at the milk first, or it should look at the word at the end of the sentence first?
What I'm saying is, now the theory they gave us that we should do the reverse, because they wanted to have milk as like very nearer or the last word to be processed.
Yes.
Last word to. However, the last word, the milk will be processed the last word if it's in the right sequence, not the reverse sequence. That's my point. Because when you go on a time step, one word at a time, milk as a last word would be the first on the top of the stack of the processing of encoder, because I goes into encoder, it produce a hidden state, and then drink goes into encoder, it get mixed with the hidden state. So we have a new hidden state where now drink has, information is there, but I got pushed down, and then milk goes into the encoder. Now hidden state get updated with the milk, but the milk itself is sitting on the top of the stack rather than the bottom of the stack as such.
Yes.
That's what I'm trying to say.
Yes. So that sentence, I drink milk. I mean, okay. So the other thing that we have to bear in mind is that these are recurrent cells, and they don't handle, the vanishing gradients and the exploding gradients issues. They can't handle like sequences that are longer. As the sequence gets longer, things get worse and worse. So really, the most important data you want is the most recent, because that'll be where it'll learn the most about it. I don't know if you quite understand what I'm saying. I mean, if you had the sentence "I drink milk," then and the most critical bit there is "I," because that's what started the whole thing off. You want that to be the last thing it processes, so that the gradients that it uses for the back propagation have that info as like the most important, and then that's why you would go in that direction.
Okay, so that's the confusion I have. I drink milk. Which is the most important bit in here, milk or I?
I would say I, because sentence is always like flow. You know, it depends on which, obviously, whether it's a left to right or a right to left language. But like English, what's at the beginning of, I mean, okay, so again, you've got an interesting point there, which is the beginning really the most important bit? And I'm kind of hypothesizing the first, 5 or 6 words in a sentence are probably the most important. They give you like a lot of direction as to what's going on. But again, that's a hypothesis.
Yeah, but then the it makes sense what you say here, but what they have described in the paragraphs, they emphasize on a milk part. They're saying milk is the most important part of this sentence, and that's the reason he reversed it in the previous section. And I kind of like disagree, but then again, like I probably wrong on some part of understanding, which I can't grasp why.
Yeah, I mean, they must have done experiments to kind of do it that way. As I said, for English, I certainly think the words that start a sentence are really quite important because they feed through to what the rest of the sentence is all about. It might be that certain other languages like French or German, maybe the first couple of words are like just kind of getting going, and then the middle bit is the most important, or the words near the end are the most important. But whatever it is, the most important stuff is what you want it to be processing the last, because the back propagation is going to work from the end backwards when it's trying to train it. So you don't want to end up having the most critical stuff like really deep down where the gradients are so small that it's not learning that stuff. But the nice thing is that these attention mechanisms, they throw all that out the window, because here it can focus on any part of that sentence it feels like, which is why obviously the performance is like so much better than some of these earlier models that we have.
Okay. Yeah.
So normally encoder decoder, you encode it, produce a hidden state, and then you use that hidden state to drive the decoder.
So with this hidden state, it's the final hidden state of the encoder, or the every timestamp step we create the hidden state and that goes to a decoder.
Under normal encoder decoder is the final state. Because you feed the whole sentence into the encoder, you take the final output, and then you feed the final output to the decoder to drive it to do that. Now, these attention mechanisms are a little bit more different, and this is where what you were just saying comes in. So in an attention mechanism encoder decoder, what happens is that at each time step, what you're computing is you're using the hidden state that's output either at that time or the previous time. And then you're making a computation against all the outputs that came, including the hidden state, and then doing a softmax on it. And you're kind of keeping this info around as being the info for that time step. So instead of just the hidden state as being output, this whole thing is what's being kept. And then what's going to be fed into this guy is actually well, it depends on the architecture, but it's either the hidden state, final hidden state concatenated, the hidden state at that point concatenated with that, so instead of like at each time step having just the raw data coming in or whatever was the label, you're actually feeding this additional info into the decoder. So the decoder's got information about the hidden state. Well, it depends on the architecture, but the hidden state as well as this additional info, which is what the attention as to what bit of the of the original encoder it should pay the most attention to, as it were. Does that kind of make sense?
Yeah, it makes sense. Yeah.
So we'll just go past this because that's sort of a description of that, and then. Yeah, so they're saying, so this was this bit where if the input sentence is n words long, and assuming the output sentence is about as long, then this model we need to compute n squared weights, because essentially at each time step, all the input words have got like a weighting so that the decoder can decide which bit it should focus on most. But they're saying, most times our sentences don't have thousands of words. They're in the sort of, low hundreds of words for each sentence. So this is still practical. So that bit was about the new attention. And that was all to do with doing this kind of concatenation operation and then computing a kind of like a softmax. And then this other chap, Min Thang Leung, he suggested, because all what we're really interested in is the similarity of the hidden state to what we should be focusing on. And the easiest way to compute similarity is dot product. So why don't we use dot product? And this is called Luong attention. And this is kind of like the modern, or also called multiplicative attention. This is kind of like the modern approach to attention is this dot product. And then they're saying this, so these guys, they compared both dot product approaches to the concatenative attention mechanism, adding a rescaling parameter, and they observed that the dot product variants performed better than the concatenative attention. So this is the dot product, and the earlier one was the concatenative. So obviously after experiments, they decided this was actually a better approach. Is that okay?
Yeah.
And there's a little diagram of all three. So the dot product is the hidden state. With the dot product against the input, they've got this slightly general one where there's a scaling factor put in the middle. And then the concatenated one is there's a tan H computed on the concatenation of the hidden state, as well as the inputs. Sorry, the outputs of the cell at that point. And then they've got a small section of visual attention, how the attention mechanisms have been used in vision as well. And this say here for image captioning. And they've shown that particularly in this step where it was trying to output frisbee, it was actually focusing on the frisbee bit. And this is quite nice actually in that a lot of these attention mechanisms, because they output all these attention weights, you can get some explainability as to what exactly it is that the model was trying to achieve. And yeah, I mean, I've seen that actually really quite impressive, because there was a lecture I attended, a webinar from some guys in Zurich who work for Thomson Reuters, and they do summarization. And then they could use this kind of attention scores to actually say why it is that the model generated these summarization it did, because it'll tell you what words it focused on when it decided to make that summary, which is actually really nice. Yeah, it was really impressive. So that's up to the section there. I don't know if does anybody have any questions or comments?
No, I'm good.
Okay, so now we come to this important area called attention is all you need. So this was this famous paper by some Google researchers and who created this architecture called the transformer, which is really improved everything, like, hugely. And they say one of the nice things about this model is that because it doesn't use these recurrent units, all it uses is kind of normal matrix operations, and there's it's much faster to train because everything can be parallelized and batched. So it says, as an extra bonus, this architecture was also much faster to train and easier to parallelize. So they managed to train it at a fraction of the time and cost of the previous state-of-the-art models. So yeah, I mean, this is what's made a lot of the modern NLP really possible on GPUs. So this is the transformer architecture. So we're just going to go through it now. So we're going to start on the left-hand side here. So the left-hand part is the encoder. So this is the kind of the encoder. Unlike the previous diagram where we had like time steps, here we're just inputting the whole sentence in one go into this guy. And the output of that, then we're feeding into the decoder, in the next stage. So the whole thing can be done kind of end to end. So here we go. So let's walk through this figure. The left-hand part is the encoder. Just like earlier, it takes as input a batch of sentences represented as a sequence of word IDs. So this is this input embedding. And it's got this kind of structure: batch size, max input sentence length. So a batch of sentences. And then it encodes each word into a 5-cell dimensional representation, and that's the word embedding bit. So note that the top part of the encoder is a stacked end time. So basically, this is one particular unit, and you'll have n number of those, one after another. And in the original paper, n was 6, but things have become a lot bigger now. I think bird base might be 6, and then bird large might be 12. I'm not sure, but yeah. So the idea is there's variable sized number of these units that you can add one on top of another. Is that bit okay? This left bit?
Yeah.
Okay.
Sorry. Okay. I think maybe they will cover that later. One was like that bit is n times, which is 6 times. So like you have a 6 heads, but then there are stacked 8 times one over the another as well.
Yeah, so the heads are actually down here. So so when it says n equals 6, those are not heads. So the multi-headed bit is within each one. And so basically this is, I'm not quite sure what they call this unit. I guess this is like, I don't know, transformer encoder unit. There's just 6 of these one after another. So, I mean, this thing is huge. If you look at it in terms of the number of neurons, obviously there's millions and millions in here. Even though the architecture is quite small. So you've mentioned multi-head in the heads. They're actually at this level here. Can you see it says multi-head attention? That controls how many heads you have. And then this whole unit, which is, I mean, these heads, and there's a skip connection, which does normalization, and there's a feed forward network, and there's another skip connection, and then there's some more normalization. And the idea is the final output from this guy is the same shape as what it came in. So you could kind of plunk just another one of these on top of it, because the input is the same shape as what this unit had. Yeah.
So you're saying multi-head would be sort of like stacked one over another 8 times or something?
No, so head is actually a slightly different concept. So imagine, so can you see here? It's got like these 3 little arrows.
Yeah.
So that's the head bit. So the idea is the same input is potentially going into 3 different heads, but you can have 8 heads in here. Say, I think the original the BERT has 8 heads in here. So the idea, the input's going into 8 different different kind of head units. Yeah. And the reason that you do that is that you don't want, because sentences are quite complex, potentially there's lots of different features in a sentence that you might want to pay attention to. So it's not, so each particular output is going to say, oh, this word is kind of paying attention to that word, and this word is paying attention to that word. But actually having multiple heads allows you to have a lot more information, because each one of them could be paying attention to different aspects of the sentence. And that's what you need to get the performance that they're getting. Does that kind of make any sense?
Yeah, so I think there is slight difference there. You see the 3 arrows which you are pointing to.
Yeah.
These are nothing but 3 arrows are the 3 different embeddings, which is query, I think, the query, index, and then there is third one. So that's what these 3 arrows are, going to multi-head. But I thought the multi-head, or like one part I'm missing is the stacked, like they are parallelly going one over the another one. That's what I was saying. Like 3 arrows are the query.
I know what you're saying, the query, K and we. Okay.
Yeah.
I mean, I'm sure that this whole notion of heads, that it actually has got multiple head units, and the idea is that these 3. Okay, I mean, you're quite right. I probably shouldn't have said that, but the heads are not stacked on top of each other. The heads are actually kind of in parallel here. And this whole unit is what's stacked one on top of another. The head bit is here, this bit here. I mean, it's all eventually getting added, and there's a feed forward network, which is kind of then bringing things back together again.
Yeah.
So that the eventual shape is the same, but it branches out here into multiple kind of head units.
Okay. All right. Yeah. That's the bit I was missing. Yeah.
Yeah. So now we look at the right-hand bit. And the right-hand part is the decoder. During training, it takes the target sentence as input. Yeah, so the input here is the target sentence, also represented by a sequence of IDs, shifted 1 time step to the right, i.e. state of sequence is inserted at the beginning. Yeah, so they've got this kind of thing where things are masked because basically because you're putting the whole sentence in at each point. They use a little bit of masking so you can't see in the future. In the decoder bit, you can only see into the past. Okay, does that make sense?
Yes, I think I know that concept. Yeah.
Yeah. It's basically because I mean this thing is not. I mean the right-hand side is kind of per time step, so it's kind of generating at each point what the next word should be, but the input to it is like a whole kind of sentence or part of a sentence.
Correct. Yeah.
And to stop it from seeing too much information, they mask out the future at each point. Yes. So this bit is iterative. It will run the number of times that it needs to generate the because I mean one of the main uses for this is machine translation. So this guy has obviously encoded all the information about the sentence for it to decode, and now this thing has to go sequentially around a loop, generating a token at each time step for the translation. Yep. And then they're saying that during inference, the decoder cannot be fed targets, so it's feeded the previously output words, starting with a start of sequence token, which is kind of normal in that, during inference, because we don't know what the final sentence should be, we just take what it last output as the next bit of the input as the sentence kind of keeps growing. Is that kind of okay?
Yeah.
Okay, so now we go into the next section. So they have. So let's have a look. So looking more closely, as you can see that you're already familiar with most components. There are two embedding layers which you've already come across, some skip connections and a normalization layer and a feed forward module. So all of these things that make this up were actually fairly well known, but it's the way they're all kind of put together is the interesting bit. So here we've got, so the encoder's multi-head attention layer encodes each word's relationship with every other word in the same sentence, paying more attention to the most relevant ones. For example, the output of this layer for the word queen in the sentence, they welcome the Queen of the United Kingdom, will depend on all words in the sentence, but it will probably pay more attention to the words united and kingdom than to the words they or welcomed. This attention mechanism is called self-attention. The sentence is paying attention to itself. We will discuss exactly how it works shortly. The decoder's masked multi-head attention layer does the same thing, but each word is only allowed to attend to words located before it. Finally, the decoder's upper multi-head attention layer is where the decoder pays attention to the words in the input sequence sentence. So this is where the input is coming in here. So this multi-head is attending to the output of this guy, but also the input that came in from the encoder. And for example, the decoder will probably pay close attention to the words queen in the input sentence when it is about to output this word's translation. Now, the other important bit that the transformer has is this called the positional embedding. It's this this guy here, the positional encoding, which is added onto the input. There's an explanation here of exactly how this positional encoding is. So actually, this positional embedding, it's quite a critical component of it because it allows you to do because transformers just put the whole sentence in one go, and words can tend to anything else. Unless you tell it what order words are, it's quite tricky for it to work out any kind of dependency between words, which is more to do with what position they're in rather than just the fact that two words are related in some way. So these positional embeddings help it out to do that. And the way they're done is using this slightly convoluted mechanism, which is to use a sine and a cosine, which are slightly out of phase. So because it's sine and cosine, then they're going to always be slightly out of phase in most places. And this is what what this positional embedding would look like for words that are. This is the number. This is the word position here. And one of the nice effects of this is that because they're slightly out of phase, virtually every position in here has got a unique combination of a sine and a cosine. But words, so it's possible for it to kind of decide to pay attention to a certain word in a certain position and then another word in another position. And so there's an interesting comment here saying this solution gives the same performance as learned positional embeddings do, but it can extend to arbitrarily long sentences, which is why it's favored. Yeah, so in theory, you could learn the positional embeddings, but this does the same performance, and you can pre-compute it as well, which is quite nice. And then there's a comment here which is going to say, moreover, the choice of oscillating function, sine and cosine, makes it possible for the model to learn relative positions as well. For example, words located 38 words apart, for example, positions 20 to 60, always have the same positional embedding values in the embedding dimensions 100 and 101, as you can figure in 16.9. Yeah, so there.
I missed the point. So what he's saying, moreover, the choice of oscillating function sine cosine makes it possible for the model to learn relative position as well. For example, the word located at 38 words apart.
Yeah, so for example, if for some weird reason it needed to know this information, that there are two words located 38 words apart, one at position 22 and one 60, and that for some reason is an interesting question to it, then because the values for the word which is at position 22 in dimension 100 and position 60 at dimension 101, they're the same values. Yeah, I mean, remember, it's a slightly, okay, so each word, I mean, let's say, I mean, P is is the particular word that we're looking at. Well, I mean, these the positional embedding is going to be sort of multi-dimensional. It could be like 784 dimensions, a bit like the rest of the word embeddings are in say BERT. And it means that the information in certain dimensions of a certain word can give it information about how far apart things are. So yeah, so this is where this bit is coming from, that in one word in dimension 100 and in the other word in dimension 101, the value for the positional embedding is the same, so that it can use that information to decide that actually these two words are 38 words apart, because of the regular kind of calculation for how the sine and cosine work. It can have that kind of information it can derive from the actual values of the positional embeddings. So I'm guessing you could probably get more complicated sort of. And so I say, if we only, and he says, what would happen if we only use the sine? If we only use the sine, the blue word at the top, the model will not be able to distinguish positions 25 and 35. Yeah, so this is where, because on positions 25 and 35 generate exactly the same, because the sine wave oscillates. And it's only because the two things are out of phase that you can get the fact that you can get positional embeddings that are different for 25 and 35, because the sine might be the same but the cosine is different, or the cosine might be the same but the sine is different. But yeah, I mean, I must confess I don't fully understand all the ramifications of doing this, but I could understand that there's more information available, but then there's still kind of values with the sine and cosine. For instance, here the sine and cosine are the same. Here the sine and cosine are the same. Here the sine and cosine are the same. So yeah, I mean, okay, there's interesting features in there, but I don't know what the impact of that is on this embedding.
Yeah, but those are only two waves, and we will have here a lot more. So
okay,
at any position there would be like different embeddings. So we will have a unique embedding for each position.
Oh, okay. So because there are these numbers, so there's a word, okay, but then the dimensions in here as well, and then yeah, okay. Well, yeah, maybe that does make sense, that each one of these is actually going to be unique in some way. It might be that the sine value is the same, but the cosine value will be different. Okay. And then there's a little bit of explanation about how you would create one of these guys, because there's no built-in positional embedding layer. So multi-headed attention. So this is the critical bit. To understand how a multi-headed attention layer works, we must first understand the scale dot product attention layer, which it is based on. Let's suppose the encoder analyzed the input sentence, "They played chess," and it managed to understand that the word "they" is the subject and the word "played" is the verb. So it encoded this information in the representation of these words. Now, suppose the decoder has already translated the subject and it thinks that it should translate the verb next. For this, it needs to fetch the verb from the input sentence. This is an analog to a dictionary lookup. It's as if the encoder created a dictionary. Subject is "they," verb is "played." And the decoder wanted to look up the value that corresponds to the key verb. However, the model does not have discrete tokens to represent the keys like subject or verb. It has vectorized representations of these concepts, which it learned during training. So the key it will use for the lookup, called the query, will not perfectly match any key in the dictionary. The solution is to compute a similarity measure between the query and each key in the dictionary, and then use the softmax function to convert these similarity scores to weights that add up to 1. If the key that represents the verb is by far the most similar to the query, then that key's weight will be close to 1. Okay, so my understanding of this is, so a bit like he says, so let's say we've got this dictionary, which has got like subject is "they," verb is "played," and now we want to find verb. Well, we do, so one way we could do that would be to compute the dot product of verb against subject and against verb, and then use a softmax to work out which was the most closely matching. And in this case, verb will match because that's the closest. And then we can use that value. But the idea is the dictionary could be quite a lot bigger, and then each query basically you check against each of the keys in the dictionary and compute this kind of similarity measure, the dot product. Use a softmax to convert that into a probability, and use the highest probability as the one that you actually want. So that's this mechanism. Does that make sense, guys, so far?
Can you repeat that again? I totally missed that.
Yeah. So okay. So let's say so he says that let's say that so the encoder analyzed this sentence. "They played chess." Yeah. Mm-hmm. And I hear "they" is the subject, and the verb is "played." Yeah. Mm-hmm. So let's say whatever was the decoder, it's already done the subject. I mean, so basically, when it analyzed this sentence, it created a dictionary. Mm-hmm. And so the subject was "they," the verb was "played," and then I guess the noun, or I don't know what. I mean, I'm not great on POS. It was chess. So the encoders created this kind of dictionary. Mm-hmm. And now let's say the decoder needs to look up something in the dictionary. But because things are not matching exactly, because these are all vectors now, they're not discrete numbers. Yeah. What we need to do is compute some kind of similarity between each of these keys. So let's say there's a query and we want to look up verb. Okay. One way we could do would be, I mean, if all of these are like the verb was represented as a vector and each of these keys was represented as a vector, we could compute the dot product. Mm-hmm. And then use a softmax to convert that to a probability distribution, and then choose the one with the highest value as the result of the query, basically. Does that make sense?
Yeah.
Yeah. So this is going to be quite important, because this is how this whole attention mechanism in modern transformers works. This whole notion of a query, a key, and a value. So in this case, we just outputted the value as is. I mean, if the key was verb, we said, the closest matching one is verb. We'll output played. But actually, the attention mechanism, what it does is it'll say, okay, let's say the similarity measure between verb was like 0.9. It would output 0.9 of played, not like the total played, because it was only 90% sure it was a play, was a verb. So it gave 90% of that value instead of like 100%. Does that make sense?
Yeah.
Okay, so let's keep going. So it says, the solution is to compute a similarity measure between the query and each key in the dictionary, and then use the softmax function to convert these similarity scores to weights that add up to 1. If the key that represents the verb is by far the most similar to the query, then the key's weight will be close to 1. Then the model can compute a weighted sum of the corresponding values. So if the weight of the verb key is close to 1, then the weighted sum will be very close to the representation of the word played. Okay, so in short, you can think of this whole process as a differentiable dictionary lookup. The similarity measure used by the transformers is just the dot product, like in long attention. In fact, the equation is the same as for long attention, except for a scaling factor. The equation is shown in equation 16.3 in a vectorized form. So this is computing a softmax. This is the query. This is the key that is the vector of keys, computing the dot product, and then scaling it by this dimension of the keys, multiplying by the computing a softmax, and then multiplying it by the values to get like an attention matrix, which will give you kind of like what it attended to the most. Does that equation kind of make sense, guys?
Yeah.
Yep. And the main reason they do this scaling is to do with this thing called the saturation of the softmax, in that some of these numbers may get a bit wieldy. So if you divide it by, to kind of scale it down a bit to ensure the softmax is going to work reasonably well. Yeah, so this is what it says. The scaling factor scales down the similarity scores to avoid saturating the softmax function, which will lead to tiny gradients. It is possible to mask out some key value pairs by adding a very large negative value to the corresponding similarity scores just before computing the softmax. This is useful in the masked multi-head attention layer. So some things which you definitely don't want it to pick up, you can use this kind of mechanism by having a much larger negative score. So in this encode, the equation applied to every input sequence in the batch with Q, K, and V all equal to the list of words in the input sentence. Yeah, so this is how transformers works, is that these three values, the Q, K, and V, are set to be actually the same value on the input, which is a little bit non-intuitive, but we have to remember there's some weights in the middle, which are all learned, and that's why it can have do all this really quite interesting calculate, you can create interesting results on the attention because of the weight matrices that are involved as well, not just the pure dot model product. There's actually some scaling in here as well, which is what's learned. Does that make sense?
Mm-hmm.
Okay, so if we carry on, and then let's have a look. Similarly, in the decoder's masked attention layer, the equation will be applied to every target sentence in the batch with QKV all equal to the list of words in the target sentence, but this time using a mask to prevent any word from comparing itself to words located after it at inference time. The decoder will only have access to the words it already output, not to future words, so during training we must mask out future tokens too. So in the upper attention layer of the decoder, the keys K and V are simply the list of word encodings produced by the encoder, and the queries Q are the list of word encodings produced by the decoder. So yeah, so this is where, so two things are coming in here, which is the keys and values, and then one of the things is coming from down here into this attention head. So that's where so what did it say? It said what came from the decoder. So in the upper layer, the keys and the values are simply the list of words encodings produced by the encoder. Okay, the keys and values come from the encoder, and the queries come from the decoder, and that's what drives the upper bit of the transformer in the decoder. Okay, so there's a pre-built-in attention layer implementation using scale dot product attention, which is what we're talking about here. To multiple sentences in a batch, its inputs are just like QKV, except all with an extra batch dimension, because this is all batched, right? Is that okay? Okay, and then what we've got. So yeah, there's a little bit about the implementation of this in TensorFlow. There's a couple of parameters you can add in to add the scaling to the softmax, and causal, which is to ensure that you can't look at the future. So it's just okay. So let's have a look at here. So what's in so multi-head attention layer architecture. So this is so you've got this is where the multiple heads are. So each one of these is a head. So you've got the key, the values, the keys and queries going into one head, doing all the calculations, and then you've got multiple heads in here, and then there's a concatenation happening of the results, and then some further processing happening above to kind of shape it. So this is the kind of actual multi-head bit in that multi-headed attention. I don't know if anybody has any comments on this bit. It's not fantastically explained, but yeah, I don't know if anybody has any questions or any comments on this bit. So I think I'll probably read this bit. As you can see, it is just a bunch of scaled dot product attention layers. So this is what multi-head is. Each preceded by a linear transformation of the values, keys, and queries, i.e. a time-distributed dense layer with no activation functions. All the outputs are simply concatenated, and they go through a final linear transformation again, time-distributed. But why? So this is where there's concatenation happening and there's some linear. Why are we doing that?
So I have this question on this multi-head.
Yeah.
So you see the V, K, and Q. They are sort of like these are the representation of the sentences, different representation going into this multi-head. Now,
actually, I just want to correct you there. Not different, all the same. So as input, V, K, and Q are all the same.
Oh, so in a sense, it's the V, K, and Q are just one. In a sense, it's the one sentence. It's going to multi-head 8 different layers. Is that what we are saying?
Yeah, it could be. So yeah, so each one of these guys, this scaled dot product attention, is doing what we were just talking about, and it's taking as input this V, K, and Q, and they're all exactly the same. And so you're probably wondering, well, if they're all exactly the same, how is anything interesting happening? Well, there's weight matrices in here, and those weight matrices are the parameters that are being learned. So even though the inputs are all the same, it's the weight matrices that then kind of learn which bit is the key, which bit is the value, which bit is the query. I mean, I know we've given them V, K, and Q as the labels, but eventually through like learning, they will do the right thing, as it were. Yeah.
Yes. Okay. So we have a V, Q, K, and Q for like one sentence, let's say, or perhaps it's a batch, and it gets fed up. Let's say if we have a multi-head of like 8 layers, so it's going to go the same embedding going 8 times to 8 layers, and then weight matrix obviously going to get learned, and those VKQ perhaps going to get changed as the embedding. No, so the weights get changed, but embedding stays same.
Yes. Yes.
Yeah. Okay. Okay. And what's this split part is? Is this is VK and Q getting split? The embedding get divided or something, or it's just saying
not divided, but just copied. So
copied.
I mean, so there's let's say there's 8 of these. There's a copy going to this one. There's a copy going to the other one. There's a copy going to the. So they're all getting copies. And
ultimately, once from this, whatever comes out of this multi-head, that get concatenated.
Yes. Yes.
Now the question I have is, what's coming out of this multi-head? Is this a weights coming out, or the embedding get updated?
So it's the attention that's coming out. So we had this equation. Attention is the softmax of the QK, all these gubbins. Each of one of these is producing attention and an attention calculation. So, and in terms of the dimensions, it'll be the same dimension as the input, because all the matrices are like the same dimension. There's 784 basically. But each one of these is producing that. Yeah.
So when we say concatenate, so it's going to be 3 times in the length.
Yeah, it could be. I mean, depends on how many heads there are. I mean, if there's 10 heads, then it'll be 10 times that.
10 times. Okay, and then there's
actually, may I
yep. Okay.
say here? So this split thing, well, how it's usually done. So you have, for example, 8 heads, and dimension of embedding, let's say it would be 64. And in this case, usually the query and the query's keys and values are reshaped into a vector of size. Let's ignore batch size for now. Of number of heads, a sequence length, and this head dimension, which is usually would be just a dimension of embedding divided by number of heads. And then we will have different to this. So we have like reduced dimension vectors fed to each of scale.product attention, because actually where learning is happening is this linear projections, not scale.product attention is just a function. It does not have any parameters. And so we want to learn to project this keys values in and queries, everything in 8 different ways to represent like 8 different like meanings or like aspects of tokens. I don't know if I explain it, like, does it make sense what I'm saying?
Yeah. So what you're saying is let's say if we take a value vector, this is the embedding of a 64. So you're saying when we split it, the split function is going to split this 64 dimension into, let's say, eight dimension each, and then
yeah, it will be fed into that scale.product attention
8 times.
Then it will produce like each we will have attention matrix of sequence length by sequence length shape.
Yeah.
And then it will be multiplied by values, and each of this multiplication will produce a result of sequence length by dimension of value vector. And when we concatenate, we end up with the same dimension as we started, because we like concatenate 8 vectors of dimension 8.
Yes.
So
yeah, I'm not sure if I
don't know,
so let's have
a post with walkthrough through it with a code in PyTorch. I can share it if you're interested.
Yeah, okay.
And it's like
so that's the embedding. So
like everything from scratch.
Okay.
So I can.
Yeah. So there was like an explanation of what this thing was going to be doing. So if there's a query, key, and value. Yeah, I have to read that up because I wasn't sure that was like exactly right. Although, I mean, there's weight matrices. So if the shape of the weight matrix is, because you can see, so here is how they generate the query, key, and value. So they're taking the input embedding and a weight matrix to generate a query. And you're quite right that the dimensions of the query have been reduced because the weight matrix is dimension is different. And then that's going into the, okay, yeah, okay. I think I understand.
But however, the part Q, the part which we discussed was after the K, Q, and V.
Yeah, so
in a sense,
so this is where the heads.
In a sense, we're going to have the embedding first, and then embedding will have like 3 same embedding it replicated into 3, which we call it as Q, K, and V. However, and that obviously going to get learned. However, when the Q get fed into this multi-head, that get divided further into.
Yeah, so this is, for instance, this is the input, and these are the attention head weights here, which it's going to use to compute, to do the calculation. So let's have a look at where it's got the, so the attention head 0, Z0. And then we got
so in the book,
attention heads
Q, K, and V are the same as X here, because here he has like, he feds X to and multiplies it by matrix and gets Q outside. And in the book, he has like K, Q, and V, and then linear projection, which is this matrices W, Q, W, K, and all.
So yeah, so this is the one. I think this probably would get us something in here. So you see the X is the embedding.
Yeah.
So that's the initial embedding, and then W, Q, K, and V, three different weight matrices.
Yeah.
And then the Q, K, and V, which the embedding, final embedding comes in, it comes from the X.
Yeah, so, okay, so here, this is the input. So using these matrices, we compute Q, K, and V for the input.
Okay.
And then these are the weights within the head. And we use these to actually compute the attention. I mean, he hasn't, I think the calculation for how we use these three guys and these three guys to compute Z is a little bit further up.
Yeah.
And then each one of these guys is then concatenated to form the final output.
One of the confusion I have is the dimension of Q, K, and V. Shouldn't that be same as that of an X, which is the initial embedding?
Yeah, so
no.
This is the interesting bit, which
As I said,
Arthur was saying, that basically, depending on the number of heads we've got and how we want to concatenate the final output to be the same dimension as the original, we would have to change the, I mean, if we had 8, let's say, we had 8 heads, then we're going to concatenate 8 of these to form the final output. Well, these guys, the dimension has to be divided by 8 because, each one of these guys will be the same shape as these two, these guys.
But also, it's not necessary to have this dimension of this concatenated vector the same as input, because we also have output projection, which can be used to change the dimension. And this thing, when the Q, K, and V dimension is equal to dimension of X divided by number of heads, is like it's in Attention Is All You Need paper, it's explained just to keep the computational and memory cost of multi-head modules the same as it would be with like single head.
Oh yeah, okay. Yes, because essentially you could have one single head, which was the full dimension, or you could split it up. Okay, yeah, I get it.
So
it's interesting
to have all the dimensions the same. You only need to have Q and K to be the same dimension, because they are multiplied, used in dot product, and we reduce it to a single number. So we need to be able to compute dot product on Q and K. But even V can be of different dimension if you want, but that's not how it's done in practice usually.
Yeah. I don't know if any of that made sense, Dinesh.
I probably go through this the whole bit again. I guess I need to read through it. I mean, like all the small bits goes into the head, but I think when you connect them all together, I probably need to do a couple of times to get it.
Yeah, same here. I didn't understand it because I thought they were doing something slightly different to what they're doing. But now that I see this diagram, it makes sense. And what Arthur was just saying, that these two have to be the same, because because Q and K, you're computing a dot product. They really do have to be the same dimension. But then V, because you're just multiplying that by the scalar, because dot products are just numbers. That can be whatever dimension that you that you want it. But it's all but yeah, I mean, it all depends on how you're going to concatenate it all at the end as well. But yeah.
This post by JLMR is great for like gaining intuition about how it works, but I really like understand what's going on internally. I found best to just implement it from scratch and like see what's going on at each step. And I shared on Slack a link to a post where like I took that chapter from how it's called, that deep learning book by Jeremy Howard, and they had like implementation of LSTM based model from scratch. And I did the same with transformer-based language model, and I posted the link there, so you can check out the code. And like, if you're interested in like understanding the bits, I would like recommend going through it, like trying to implement it yourself, and then it's really like everything comes to places.
Yeah, cool. I think that's a good idea. Yeah. I know Wencheng did do it, so is Dinesh, if you're busy, I mean, he's I think leading tonight. He might have a better explanation, because I know he went through coding it line by line.
Yeah,
I've forgotten it, but yeah, he might still remember exactly how this is implemented.
Yeah, I'm like I usually ask for the recording, so probably watching a recording tomorrow.
Yeah. Okay, cool. So that's multi-head attention. So, and then his final bit is just some interesting papers kind of recently. So, I mean, things move so fast in this area now that even some of these are like a little bit out of date. So Elmo was a paper that was interesting in that it introduced pre-trained word embeddings that have been used. So a bit like Glove and Word2Vec, Elmo embeddings were quite nice in that they were contextual. So the word queen, for instance, in Queen of the United Kingdom and Queen Bee would actually map to different embeddings using Elmo. So, that was quite an interesting paper. And ULMFit, this is Jeremy Howard's paper, Howard paper, and they used an LSTM, but in a slightly more interesting way, and they got state-of-the-art results using this guy. So this is not transformers, but kind of an alternative way of doing it. And then there's a mention of a GPT paper, which is uses transformers. BERT paper, which is where the diagram we've just seen of transformers is actually coming from. And that's about it. So that's near the end, really.
Yeah.
Yeah, I mean, this area is just current state-of-the-art research. So I know it's really hard to get your head around it, particularly, if you're not really into this area.
Yeah,
but yeah, it's really interesting.
Arto, you mentioned you would be interested to show the code implementation step by step. I would be very interested to go over it. Maybe, what do you think, Arshad? Maybe we can spend that.
Yeah, I mean, the NLP paper session is the sort of thing that we could do. Do that with that.
We can, yeah, I can ask more question, or maybe we can just do step by step to clarify what's in there. I think more we ask or discuss, more it gets into our head. I think overall, this is the second or third time theoretically I'm going through it, but it's always a good idea to walk through code by code, bit by bit, just to get a good idea. So I'm more than happy to join tomorrow if Arto, you're happy.
Yeah, sure. I can try to like take like this walk through by line how it's implemented and why some decisions are done. So I shared that like explainer, and also I can share a link to the repo we use for this reformer implementation, and we have there also a standard transformer implementation from attention is all you need, and I can also walk you through that, and it's yeah, sure we can do that.
All right, let's do that tomorrow then.
Yeah, that's great. I mean, the other paper I was reading was very high level, so it didn't really have a huge amount to kind of say that would be of really interest. So yeah, this would be great, and I can find a slightly better paper for next time.
Yeah, maybe I can do it in half of our time or something. And,
no, I'm happy to give the full session to it because I think this is really important, and you know, and
you can take as much as time you want.
Yeah.
Yeah, good. Actually, like I spent quite a lot of time on this some time before, and I feel like I have a pretty good understanding of what's going on inside this model. So
oh, fantastic! So let's go through it. I'll go through the link which you sent, the GitHub link. So I'll go through it just to have a initial understanding, and then obviously we'll have a walkthrough tomorrow again with you.
Yeah, sure.
Okay, great, guys. So I know it's about 8 o'clock, late for you guys, but yeah, it's a really great session. Looking forward to tomorrow.
Absolutely. Thanks very much. Thanks, Arshad and Ato. Thanks very much.
Yeah.
Look forward for tomorrow.
Thanks then. Great. Bye.
Cheers, guys. Bye.